Hey everybody, welcome to 1 Minute Math, and today we're going to do a full explanation of the chain rule. This is a calculus concept, and the context here is that we're finding derivatives of functions. So hopefully at this point in time, you're at the point where if I said find the derivative of x cubed plus 2x squared plus 5x, you would know how to do that. We're going to do the product or the power rule here, bring every power down, and then decrease it by 1, multiplying as we go. All right, if that's the point that you're at, and now in the chain rule, our challenge here is going to be what happens if I give you a function that I would like to find the derivative of, but it's not just a polynomial, or it's not just even a simple operator. You might even know at this point that the derivative of sine x is cosine of x, but what if I said I'm looking at not just sine x, but sine of x squared? What is the derivative of that thing? Composite functions here, right? We've got a function inside another function. We want to find the rate at which it is changing. And when I say prime here, what I really mean is the rate that it's changing with respect to x. All right, so we're going to first contemplate this as we look at, like I just said, the derivative of sine is cosine. If that's not a property that you were familiar with, you can take a look at it right now here on this page. You can see in red we've graphed sine x. And the places where sine x has a derivative of 0, because it is flat, are the places where cosine has a value of 0. And places where sine right here is increasing, so cosine will have a positive value. And you can even verify, if we zoom in here, it's pretty clear that the slope of this little segment here is going to be 1. You can see its rise over run is about 1. And the value of cosine at that point is 1. So all of this stuff checks out, and we have the derivative of sine is cosine. Now, the first thing we're going to do, we want to make this a function of a function. Instead of sine x, let's look at sine x minus 1. I'm just going to take my sine graph and shift it to the right by 1. And if I ask you what's the derivative of that function, I would be looking for something that it has a value of 1 right here, has a value of 0 over here, it's a value of negative 1 down here, and hopefully you would agree with me that that is indeed cosine of x minus 1. It's the cosine graph just shifted to the right one. So let's go back here and write that down. So d over dx, this means find the derivative of, say find the derivative of sine x minus 1, we get cosine x minus 1, and our first thing we want to note here is that this inside function did not change. When we take the derivative of an outside function in this composite function line, when we take the derivative of the outermost function, we want to leave the input function, the function that is inside that thing, we need to leave it alone so that we are putting into our derivative, our derivatizer, if you will, right? The thing that tells me what the slope is, the values that I put into that, I want to be the same as the values that I'm putting into my original function. In other words, we want to talk about corresponding inputs, and therefore that inside function must stay the same. So now let's go to another one. Instead of sine x minus 1, let's go back to our regular sine x, there's where equals sine x. I want to talk about sine 2x. Right, so sine 2x, the relationship between sine x and sine 2x is simply that sine 2x has been squished. It's twice as, it happens twice as frequently. All right, its behavior needs half as much x to achieve the same output as the original. And it is natural to think, well, perhaps the derivative of this thing, if my last example is anything I can extrapolate from, perhaps the derivative of this one is also going to be cosine of 2x. And we're not that far off, right? By keeping the inside function, by keeping that input function the same, we've guaranteed that the zeros of cosine, the zeros of the derivative, happen at the horizontal tangents of the original, that on the right x intervals, right, this sine 2x is increasing on this interval that I'm highlighting, and that is the same interval on which cosine 2x is positive. All those things line up, so we haven't done anything wrong yet. I just think we're not done. And if you're wondering why we're not done, let's look right here at the origin. The reason cosine was the derivative of a sine, and that worked out so perfectly, is because the slope of y equals sine x at the origin was exactly 1. What do you want to guess the slope of y equals sine x is at this, or y equals sine 2x is at this origin? And it's not 1. If you guessed 2, you're correct. And we can see that fairly easily. If we go back and forth, there's my original. The red thing is sine x. The black curve, the curve that's traced in black, is sine 2x. And it's kind of obvious that it is twice as steep. So that means while cosine 2x has the right signs and is positive on the right intervals and like the x values all line up, it's just not tall enough. But now it is. Let's look at that over here. All right, so if I've got derivative of sine 2x, I have cosine of 2x. That got the right position, and then times 2 to get the right output values. And what would you say is the relationship between 2x and 2 from a calculus perspective? And hopefully you agree that that's the derivative. All right, here's my generic formula. If I have the derivative, if I'm asked to take the derivative of f of g of x, I'm going to differentiate that outermost function, like sine became cosine, and leave the innermost function alone. But then I'm going to multiply by g prime of x. Right? We could think of this like a chemistry style conversion, unit conversion, if we wanted to. F prime of g of x is measuring, that's going to give us the rate at which f is changing with respect to its g inputs. So I'd be maybe going like meters per hour or something, okay? And then if the g told me was a conversion between hours and seconds, then the g prime, that would take that meters per hour, multiply it by hours per second, and give me a meters per second output. This makes sense in my head. F prime of g of x measures the rate at which f is changing with respect to g. G prime of x measures the rate that g is changing with respect to x. So f prime of g times g prime measures the rate at which f is changing with respect to x. Let's see this in action. Algebraically, these are pretty straightforward algebraically. If I ask you for the derivative of, let's do another sine one, sine x to the 5th plus 3x. I'm going to differentiate the outermost function. We'll notice we've got 2 functions happening here. Okay, I'm going to put that in a different color for now. I'm going to differentiate the outermost function first and leave all that inner stuff alone. It has to stay the same so that my inputs are the same. And I'm going to multiply by the derivative of the inside. In this case, 5x to the 4th plus 3. That is my final answer. Let's put one with the sine or the cosine on the inside. If I ask you for the derivative of square root sine x. All right, so we're going to start by finding the derivative. Here, the outermost thing is really obviously the square root. The derivative of a square root of something is like that thing to the 1/2, so we're going to do the power rule. 1/2 times inner function to the negative 1/2. We leave the inner function alone first, and then we multiply times the derivative of the inner function. Sometimes sines and cosines, they get real tricky when we use this shorthand. If I ask you for the derivative of sine cubed of x, you might be familiar with this notation and maybe you're not. We can all agree that if I wrote sine x cubed, this equation, this expression is very vague. It's not clear if I mean, do I mean sine of whatever x cubed is, or do I mean I take the sine of x and I cube what that answer is? So in order to avoid that confusion, we say this guy, if I had sine to the n of x, that is shorthand for sine x raised to the power of n. Right, so I'm remembering that this means sine x cubed, and then it becomes a little more obvious that to the 3rd is my outer function. 3 inner function squared. Inner function here is sine, and then I multiply by cosine. There is a classic error on these things. All right. Every so often, more than every so often, I would say 1 out of every 2 responses I read, at least on the first time we have this. If I'm giving a test in class on the chain rule or a quiz on the chain rule, every other response is going to say 1/2 cosine x to the negative 1/2. And that is just categorically false. That's not the correct way to differentiate things. There's this very classic trap of over-differentiating. But you got to remember that you can only take the derivative of one function at a time, right? So if I'm differentiating the square root part, I'm not allowed to differentiate the sine part in that same step. I've got to like hyper focus on what is the rate of this one thing first, and then multiply by subsequent rates. We're going to see one more here. Let's put three functions together. Let's have a chain of three links. So let's say I've got f of x is, how about sine of square root of x plus x all to the fifth. All right, and I'm asked to find f prime. I've got three links in this chain. I've got something to the fifth, I've got a sine, and then I've got that innermost function. So I'm just going to follow my chain rule. Take the derivative of the outermost thing first, which is that. And that's all I can differentiate in that step, so everything else has got to stay the same. Alright, next step. Now I multiply by, my next function is the green one, and the derivative of sine is cosine. And I just differentiated sine, that's all I'm allowed to take the derivative of in that step. So I got to leave those innards alone. And now finally, I can take the derivative of root x plus x. Now I'm just going to quickly make some shorthand of this. You've seen this once before already today. If we do a little algebra here, we can see that 1/2 x to the negative 1/2 turns into 1/2 roots of x. You do not have to simplify that expression, but it's kind of good to, it's good to know that the derivative of root x is 1/2 roots of x. It's good to know that the derivative of 1/x, yes, that is like saying the derivative of x to the negative 1, and yes, that is negative x to the negative 2. But it's also good to know that that is negative 1/x squared. We see these frequently enough that it's good to be familiar with their colloquial representations. All right, anyway, here is my formula for f prime. I'm going to point out here that derivatives get more complicated. I can have a very condensed function, and when I ask you to take the derivative, it just grows and grows and grows and gets more and more complex. And that's an accurate observation, and it's okay if we kind of lean into that and understand that, especially when we're looking at anti-differentiation later. Sweet. So what I would like to do now, we have seen the algebraic part of this, all right? It's time now to look at the numeric part. Functions are not always presented to us algebraically. And this comes up frequently on the AP exam, or if you're in a college calculus class, I'm sure that your professor is going to come up with some of these things. It's really important to be able to apply the chain rule and other derivative rules in non-algebraic contexts. Functions can be presented to us algebraically, but they can also be presented to us graphically and as numeric tables of values. And it's important to be able to apply what we know. So this is a good one. This 2003, this was an FRQ, and before we hit that exact question, we're going to practice with some of these. Okay, so we're going to skip number 17 here. This is my underlying information. This is the stem of this problem. I've got two functions, g and h, and I happen to know that g of 5 is 9 and g prime of 5 is 6, and h of 5 is 5 and h prime of 5 is negative 4. So let's look here at number 18. I'm asked to find f prime of 5, and I'm noticing that f is a composite function. There's a function inside a function. The outermost thing is squared, so f prime is going to start by saying 2 times blah blah blah. And my chain rule, if I just kind of by rote plug the chain rule in here, I get that f prime would be 2 times h prime. Basically 2h to the 1 doing the power rule, the derivative of something squared, and then h prime by the chain rule piece. So f prime of 5 will be 2 times h of 5 times h prime of 5, and I've got all those values right here. H of 5 is 5, and h prime of 5 is negative 4, and that's my answer. If you feel like you absolutely have to simplify it, it would be negative 40. Let's take a peek at 19. We'll just set up 19, and then we'll take a look at 22. And after that, we're going to go over to that AP exam question. All right, here again, I've got a function inside a function in 19. Square root is on the outside. So f prime is going to be 1/2 blah 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 to the negative 1/2, and my function here is g, and then times g prime because of the chain rule. So f prime of 5 would be 1/2, what's g of 5? G of 5 is 9, 1/2 times 9 to the negative 1/2, and g prime of 5 is 6. I'm going to leave it there. There's really no reason to compute that further unless your teacher is adamant that you can't leave things in numeric forms like that. I wouldn't risk making algebra error. All right, and now 22 is kind of the classic one. F prime, if I just kind of by rote apply the chain rule, g prime of h of x times h prime. That is like literally what the chain rule says, and then I could just plug those in, and this is going to take a little bit of effort on my part because to compute g prime of h of 5, that takes a couple steps. H of 5 is 5, so g prime of h of 5 is 6. And h prime of 5 is negative 4. Beautiful. Okay, we could do 21 as well, but hopefully you've got the idea of how we use this numeric, how we use these numeric values. Now let's take a look at this one. This was a question on the 2023 AP Calculus AB exam. It was question 5 on the FRQs. It had, I think, 3 parts. I think there was an A, B, and a C in the same trap. If you've been reading this while I've been yapping, it says f and g are twice differentiable. That's important later in the problem. And we have the table of values up here telling us f prime, g, and g prime for lots of values of x. And we are asked to find h prime of 7, knowing that h is f of g of x. And now you've been watching this video this whole time. You know that this is going to be the chain rule. F prime of g times g prime. So h prime of 7 will simply be f prime of g of 7 times g prime of 7. Okay, g of 7 is 0. G prime of 7 is 8. F prime of 0 is 3/2. 3/2 of 8 is my final answer. And again, if you really wanted to compute that, you should get 12 as your final answer there. Cool. This has been the chain rule. I hope that you find it helpful. I definitely prefer to use the chain rule rather than the quotient rule or the product rule whenever I can get away with it. Yeah, keep watching.